Alright, hello world. Um, so today, I'm looking at the next couple. So what happened last time is I just started talking about Gaussian binomial coefficients. These are this bracket nk. That's defined a little differently. You need to be given a q. So sometimes they'll emphasize the q, but often not. Anyway, you have some seemingly small q value. Avoids roots of the denominators, right? So the denominator is 1 minus q squared, etc. So we're avoiding zeros of those, of course. So that's why he makes a comment about roots of unity. I guess roots of unity on the order of k would be bad, right? But k is changing. K is less than or equal to n and greater than or equal to 0. For 0, we just get 1. I think we already showed it was symmetric. So I did the first 3 last time. I was kind of stuck on the last one, except that I just didn't notice that this is a power series, obviously. And this left-hand side is really, it's clearly satisfies some functional equation. So if you just let f of x be this left-hand side and figure out that, what functional equation it is, you can then assume that it's a power series, and you can figure out what the coefficients are, and they'll be this. So it's actually not too bad. If you don't do it that way, you're there thinking like these coefficients are the sum of some selection of these powers of q. So I guess it's good to realize that that's what you're looking at here when you deal with this generating function. But anyway, let's see if I can tackle a couple of these. Hoping to get at least the first two. 60.4 is, I'll put it on your screen. 60.4 is basically just an analog of Pascal's identity. And 60.5 is pointing out that this function is a polynomial of degree k times n minus k. So I haven't done these before. I did take a quick glance at the answers just to see there was no surprises, but I still don't really know. Should make it a little smoother, but I still don't really know how to do them off the top of my head. Well, one thing I do know. So here, let's see. It's under screenshots, maybe. Well, that's all right. I'll just show it to you here. The result from last time, 60.3, you can use that to get this one. So we're trying to prove this identity, but notice that this coefficient just showed up in the previous problem. There it is, right? Shows up right there. So in the back, he said you can prove it directly, which is what I would have done. Or you can use this identity we just proved, multiplied by 1 plus q to the n, x. Okay, it's going to tack on, it's going to change your n value effectively to be n plus 1 in the formula, but it also does something kind of obvious on the right-hand side. It gives you two terms. It gives you 1 times this plus q to the n x times this. So it's going to shift, like, it's going to shift the k value, and it's going to change this q exponent, and so it looks like it very well might give you exactly this result from 60.4. Yeah, it does. So on the left-hand side, you'd have the same old formula. So then when you just equate the coefficients. So this is basically a one-liner if you use 60.3. But I'll see if I can get it directly as well. So 60.4. Yeah, you're looking at it up there. I wouldn't have done that. I would have tried to do this just directly. But maybe I'll first do it the easy way that I just described. So is this q to the n minus k plus 1. So the easy way is noting that from 60.3, yeah, I have it here. This equals this. So the product from 1 to n of 1 plus q to the k minus 1 x, right? That product is the same as the sum. And then you put your little Gaussian coefficient guy, but then you also have to put a q to the, and it's like the sum of the k values times x to the k. Let me just double check that. Yeah. And this is a regular sum from 0 to n. So we proved this last time. I was just talking about that. Like, the way you prove it is to let this be a function, like call this f of x. Notice there's a functional equation that it satisfies. If you just multiply this by 1 plus q to the n x, you'll see what it is. Actually, f of qx instead of f of x, for instance, we'll scale this and it'll change. You'll be missing the first term. And anyway, if you it's very similar to what you get if you multiply by 1 plus q to the n x. So something like that is the recursive equation, or the functional equation. And then you just assume it's a power series and you solve for the coefficients and you'll get these. It's actually not bad. I think I just said exactly all that 2 minutes ago. Anyway, so suppose we know this. I'm trying to prove this, but you're seeing these coefficients right there. So what we could do is multiply both sides by so like on the left hand side, if we multiply by 1 plus q to the n, it's changing this formula to be, you're changing n to be n plus 1. So multiply by 1 plus q to the n x on both sides. And what's going to happen is on the left you get a whole new formula. Like, we know it's supposed to be, the left hand side would be this formula but with an n plus 1 plugged in. So this becomes n plus 1k, right? That's that part. This stays the same. That actually doesn't change. The x part doesn't change. So that's our left-hand side. If you multiply this by 1 plus q to the nx, you just get a new formula, but you're replacing n with n plus 1, effectively. The right-hand side does change, right? You can distribute this stuff against 1 and q to the nx. So I haven't seen exactly what the q to the nx is going to do. But the fact that there's an x there is going to shift all the k's backwards. You know, we'll see what it does. The right-hand side, you get this series, you get one of it. And then you get q to the n x of it. So this is still 0 to n. And then again, it's still 0 to n, I suppose. You can leave this stuff. But now we're going to have a q to the n times this business. So it's like same as it was, you know, plus n outside of that fraction. And then this becomes k plus 1. So we're going to adapt this, like, so I can write it as a single. I'm just going to change it so that we have in terms of x to the k instead of k plus 1 here. So all we're going to do is subtract 1 from k. Other things sort of take care of themselves. Like here, you want that when you plug in 0, you get 1. So we're going to reindex this to make it start at 1 and end at n plus 1. But of course, when you do that, like when you do that, these coefficients become 0. Well, 1 doesn't, but at n plus 1, it doesn't make sense. Choose n plus 1 becomes 0. He even explicitly says that in the definition. It equals 0 outside of this range. So as part of the definition, you know, at n plus 1, which is where this guy is going, you're not going to get any contribution. You're going to get 0 there. Yeah, that's about it. What else? At 0, you'll get, or sorry, not at 0, at 1, right? You'll get x to the 1. Never mind. You will have a contribution from that term. I was just thinking like, oh yeah, right. So when we include this 0 and we plug it in over there, this is going to become -1, right? Once I reindex, this k value is going to be shifted back. So I'm just saying this series right here, you can replace the k plus 1 with k, or you know, replace k with k minus 1. And yeah, it's going to change your index, but it actually doesn't affect anything. We can actually start from 0 and stop at n. It's no problem. So this part we're not going to touch, but this part I'm going to reindex, and it's the same as 1 to n plus 1 of, I suppose it's k minus 1, right? So that means this changes. That's fine. It's k minus 1, k minus 2, plus n. And then this goes back to k. That was the whole point, is that I want it to match up with this so that we can put it in one. I can have one coefficient in front of the x to the k. So that's why we're doing the reindexing over here. And then what I was observing is, when you plug in n plus 1, I meant to say into this, if you plug in n plus 1, into this, it'll give you 0. And if you plug 0 into this one, it'll give you 0. So there's no problem with the fact that it'll, you know, if I change it to 0 to n, it's still correct. What I'm a little irritated by is what I'm a little annoyed by is, did I mean to do that? I do, right? Yeah, I added 1 to the value. We could make a new variable if you want to explain it clearer, but like when you plug in 0 here, you're supposed to get 0. When you plug in 1 here, you get 0, right? You're supposed to stop at n, and here you stop at n. So this is correct, what I wrote here. It's just bugging me because I'm not, oh no, it is supposed to be n plus 1. Right, it's a new formula. It all uses n plus 1. Okay, good. That makes sense. I was like, why are we stopping at n plus 1? And again, what I was saying is, it's okay to change this index to be also stopping at n plus 1, because when you plug it into this coefficient, it's going to give you 0. It doesn't actually break anything. So, hey there, Slight GPX. Thanks for hopping in. So this right-hand side is, I guess it's stopping at n plus 1 now, but your coefficients are, unfortunately this stupid q thing is in the way. So I guess I should discuss, like, how does this change? Because we would normally have, q, well, let's just start writing it. Here you have n choose k, and then we have this new thing, n and choose k minus 1, which you're seeing there on the screen. That's what we wanted to get. Clearly the difference is that power of q, right? So yeah, before I need to write something here for it to make sense. There'll be a power of q that scales this to make it look like that. Because normally we have this. So yeah, so what is missing from, I mean, how do you write this in terms of this power of q? There's an n that isn't normally there, so that's part of it, q to the n. This guy's got an extra n, first of all. And then the difference is, let's see. I'm saying, like, what is this divided by this junk? What would you get if you divided those? And you can see it already, there's a minus 2 there. This is k times k minus 1 over 2 is the original stuff. So I'll keep writing, but it's kind of clear. It's kind of clear what it is. See if there's another way to. Yeah, we could deal with the fractions, but you can also just see, you know, this equals q to the what. But you can also just see that, like, you're off by this factor right here. So if we distributed k times this gives us the original stuff that I'm talking about, and then the extra stuff is this minus 2 times k minus 1 over 2. So it's really just k minus 1 is what's missing. Like, what I'm saying is our new guy is the original stuff minus 2 times k minus 1 over 2, like that. So to make it look like this, we're going to multiply by the sort of opposite of this. The missing factor is q to the 2 k minus 1 over 2. It's q to the k minus 1. If I multiply this junk, oh yeah, I guess we want to go the other way. If I multiply this by that, it'll look like our original stuff. So apparently, so yeah, it's backwards. Anyway, you get the idea. It's minus k plus 1. It's the negative of this. Right, so let's just double check that. If you multiply this by the original term, the original power of q, right, you're going to add an n, and you're going to be subtracting k minus 1. You're going to be doing this to it. You're subtracting k minus 1. Yeah, this is what you get. So if you multiply by q to the negative k minus 1, it'll look like this, and it'll be this new term that we had over there. So yeah, this is right. Anyway, that's about it for one proof of this guy. I was going to try to do it directly as well. Right now what we're seeing was 0 to n plus 1, n plus 1k, in front of the q sum x to the k, right? So if you just equate these coefficients, that's the proof. That's the end of 60.4. So that's the easy way to see it. But I wanted to see, like, I wouldn't have thought of that necessarily. I was just going to do it directly from the definition. So let's see how easy that is. It should be pretty straightforward, I would think. This definition is kind of weird. If you weren't here last time, it is this. If you're not used to it, so it's called a Gaussian binomial coefficient instead of a regular binomial. You probably are familiar with the binomial coefficient as like factorials, right? N factorial over n minus k factorial, k factorial. But yeah, this is different. Although it is very similar. And I guess if you've had sort of advanced combinatorics, you've seen this thing. We'll probably see an application next time, because like it seems to relate to, I don't want to call them zigzag paths, but like yes, they start, like, it seems to relate to traveling on a lattice. I don't know if you've ever talked about like the taxi cab metric. Um, something that definitely comes up in like a discrete math class, or I don't know, combinatorics for sure. Um, anyway, suppose you're traveling from like one point to another on a grid, and you can only move east and north, right? How many paths are there? That kind of question. Anyway, so I don't know the connection yet. I haven't done this stuff before, but um, this Gaussian binomial coefficients has something to do with. I mean, you can use it to count these types of paths for some reason. Not familiar with that yet, but we'll probably do that next week. I was just working on these two problems for today, maybe 60.6 if I get to it. But we're just working on 0.4 right now. So I was going to use this definition, see if we can get that identity that I just proved, see if we can get it just directly from the definition, how easy that'll be. So the normal definition right here, this guy is, well, let's just do it with n plus 1 first. You start at the n value, this is upstairs, and then you decrease by 1 all the way down to, I want to say n minus k plus 1, right? Yeah, that's the numerator. You want to go all the way down to n minus k plus 1, which I guess I could just remember as, that's k factors upstairs, right? Here's the 0th, here's the first, all the way up to the k minus first factor. So there's k factors of 1 minus q to some power in the numerator. Same story downstairs, but they're a little easier to remember. They just increase. So in my case, if we had n factors, you actually stop a little short, right? It's n minus k minus 2 this time. Or, n minus k plus 1. But because it wasn't n, it was n plus 1, so we're going to have plus 2 instead. Like that. And then downstairs, it increases, and we stop at k. So again, k factors here, and hopefully k factors there. Yeah. All right, so this junk is this left-hand side, and I want to show that that is equal to the usual formula plus this weird formula times a power of q. I'm not seeing that, but this must split up somehow, right? Like, maybe I can... Like, this one stops short. I need to make it look like that. So I need to introduce this denominator. Like, I need to multiply this by 1 minus q to the k over 1 minus q to the k if I'm going to hope to add it to this thing. Anyway, you'll see what I mean, I guess. So the numerator here is, we start at n, and we decrease down to minus k plus 1, and then downstairs you get 1 minus q up to 1 minus q to the k, right? That's that part. But then this part, it stops short. It stops at 1 minus q to the k minus 1. So that's what I was mumbling about, like, I'm going to have to multiply by 1 minus q to the k on the top and the bottom here just to even be able to add those. And the numerator is still n, so that's nice. It has the same numerator. N minus k. Oh, no it doesn't. No it doesn't. The k value has changed. So if you're subtracting k minus 1, it means you're adding another term, so it stops there at 2. N minus k plus 2 instead, because of that part. Right? So if instead of k you're plugging in k minus 1, it's actually minus k plus 1. So instead of plus 1 it becomes plus 2. So alright, that's correct for this chunk. Then don't forget there's an extra q on this term. I don't know what to do with that other than like distribute it, right? But we've only got, I guess we've got k minus 1 factors. That takes care of that chunk. minus k. So, okay. So we could put the q's downstairs. We could put a q in each one of these. And then upstairs you have n more of them. Yeah, I just don't see it. But anyway, clearly one thing we got to do is multiply and divide by 1 minus q to the k. Can I multiply that by a power of q to do something nice? Another thing that's missing is this guy doesn't have that term, that factor. Or you could probably phrase it the other way around, because this is actually a smaller number. This numerator is missing that factor. Huh. Well, anyway, this looks like it must be easy, right? There's like nothing else to do with it. You just have to somehow add this fraction, add these fractions together, and it'll somehow equal this. Oh yeah, we started a different one too. Huh. Alright, well at least the denominator is nice. It's kind of the same. So I guess the question now becomes, like, we're going to multiply by this denominator on both sides. It's going to cancel here. Here it almost cancels. You get an extra factor of 1 minus q to the k. So first thing I'm going to do is multiply by the denominator this big product of k factors, right? So we can just look at the numerators. And then at that point I can see, like, this guy on the left is missing, it's missing this factor, and it's missing this, yeah, this factor. How did that happen? Isn't this a, yeah, these are decreasing. So yeah, it seems to be missing this and that somehow. Weird. But, so if we multiply with the denominator, all I have to prove is this junk oops, 1 minus q to the n, 1 minus q to the n minus k plus 2. We want to see if that's equal to, now when I multiply by this big product of k factors, it cancels with those k factors. So here's the first part, coming from this guy. These are again decreasing down to n minus k plus 1, because that's just the usual definition. But then, when you multiply this junk on the second guy, he doesn't have that last factor. So that's the one that kind of survives and is in the numerator now. Everything else canceled. So for the second term, this term, we're getting 1 minus q to the n. I don't know where to put the k, because it doesn't actually show up. There's a little gap here, right? There's a big gap there. Anyway, it goes all the way down to 1 minus q, n minus k plus 2. Then we've got this q, and we've also got the extra factor that I was talking about. So there's this extra 1 minus q to the k, and there's this power of q that is supposed to be there, q to the n minus k plus. I'll just put it here, q to the n minus k plus 1. So yeah, I'm supposed to show that this equals that, which is, I guess, going to be easier to see, but I don't see it. Alright, well, so what's different about it? This guy on the right has this 1 minus q to the n, which this guy does not. I mean, I could start dividing, frankly, right? If we divide by all these, I'll get 1 on the left. At least maybe that's something. If I divide by all these, you will see all of them. You won't see that one. That one doesn't show up yet. Oh, it shows up over here, though. It doesn't show up here. But anyway, you can see that 1 minus q to the n is in... Okay. Oh, no, it's right there. It's right there. Okay, so there's a couple that are extra. Maybe I'll leave them on the left for now. But there's all these guys in the middle, right? There's all these factors in the middle. Q to the n, q to the n minus 1, q to the n minus 2. Those are all over here, except for, like, the n's are not quite the same. But, like, n is there. N minus 1 is there, all the way down to this guy. like this guy is also here. He's in this group. I didn't bother to write him, but so we can at least divide by, I'm going to leave the n plus 1 on the left, but we can divide by this one and this one. So we're going to divide by these extra factors. And on the left we'll have those two. And on the right, a bunch of them cancel. It looks like even this one cancels. So we're going to have a 1 plus, so this guy's gone. Like this whole term is just gone now. This one canceled all the way up to the one previous to this, but this guy's still there. So this guy is still there. I didn't divide by that term. I divided by the terms 1 minus q to the n, 1 minus q to the n minus 1, all the way down to this guy, 1 minus q to the n minus k plus 1. So that's why they're all missing from this left-hand side now. We're good except for the q's, right? So we've still got this extra guy that was just introduced in the previous step. And of course we've still got the original hypothesis part that says there should be a q to the n minus k plus 1 there. All right, are these equal somehow? Well, what? All right, what if I did distribute this? Here you get q to the n plus 1, right? Oh, shit, that's that guy. Wait, so you get, but this doesn't match, which I guess is good because these are not equal yet. Huh. Is that a good thing? Maybe we should do that. All right, if I combine these, you're seeing this, which is pretty ugly, but then the next part is this guy, q to the n plus 1, right? When you multiply these q's. Anyway, this is definitely much gorier than what I'm calling the easy way. Just using 60.3 was a lot easier than what I'm doing here, punching, shuffling these factors around. I mean, do you think we should just distribute and it'll happen? Because like here you're going to get q to the 2n minus k plus 3, which is what you get here too. Do you think it's worth just distributing when we got an extra? Let's see what you get. Yeah, I think, well, we do have this as a factor, so shouldn't I be able to like, not quite. It's not quite a factor, right, because of the plus 1. If I divide by it, maybe that'll be nicer. We'll get 1 over it plus this. This equals 1 over this madness plus this. Yeah, it doesn't really look that nice. All right, well, the most straightforward thing to do is just expand both sides, right? Just FOIL this out. That's the most obvious thing. So on the left-hand side, we're going to get 1 minus q to the n plus 1 minus q to the n minus k plus 2, and then you get the plus of the one I was just talking about, 2n minus k plus 3. That's the left-hand side. The right-hand side, there's a 1 here. Then there's this business. We get q to the n minus k. Getting a little nervous here. Q to the n minus k plus 1. Oh, does that cancel maybe? I guess we'll see. maybe, no, something has got to cancel. I don't see it. Did I miss? Nope, you didn't. No. Alright, fine. Anyway, 1 plus, here's the first term. Here's maybe the middle term is q to the 2n, you know, this guy that we just wrote. 2n, wait a minute. It's not the same thing that we just wrote. Yeah, it's just not the same. Alright. That's weird, man. What am I going to do with this? 2n minus 2k plus 3. I just thought it would be the same. 1 plus, so we got this guy, we got the middle guy. We're going to do the outer one now. And the last one is minus q to the 2n. That one's the same. 2n minus k plus 3. So the ones are gone. This is actually not actually gone. There's 2 of these. That's a nightmare. Minus q to the n plus 1 is gone. Do we have an n minus k plus 2? Not really. Okay. Well, so we're getting, like, the 1 and these first 2 terms are gone. They agree with the terms on the right. We could maybe factor. Unfortunately, this stuff just doesn't quite. So if I add and subtract, we're getting that 0 equals, if I add this first one, we're going to have n minus k plus 1, n minus k plus 2, and this guy, and then we have minus 2 of these. Or I guess another way we could have phrased it, well, I'll write it separately in a sec. But yeah, what I'm getting is q to the n minus k plus 1, q to the n minus k plus 2. Starting to feel like I made a mistake. 2n minus 2k plus 3. And then I subtract this term, which happens to match this one, so we have 2 of those. Right? Why would this be 0? Clearly I made a mistake, right? These are, well, they're not quite bigger. We don't know that, this 2n thing here. Anyway, if this were true, then we would be done. But this was supposed to be, this is probably pretty straightforward, so did I screw something up? N plus 1 down to n plus 1 minus k plus 1. Yep, that's right. First term is n minus k plus 1, and then this one is the same, n minus k minus 1 plus 1, which is that. So I didn't make any mistakes on the setup. This is the right value, I presume. N minus k plus 1, yep. Alright. Yeah, I don't think I made a mistake, but I don't see why this would be true. So another way we're looking at it, another way to phrase that is that 2q is that 2q to the 2n minus k plus 3 is supposed to be equal to the sum of these 3 powers of q. I don't see why this would be true. Minus k plus 1. Q to the n minus k plus 2. And then there's the weird one, 2n minus 2k plus 3. 2n minus 2k plus 3. So evidently this is true. For all q, really? That doesn't sound right. I mean, really? Like, why would this be true? Makes me wonder if I just somehow made a mistake back here. So I multiplied by the denominator. Canceled. Didn't quite cancel here. We got an extra factor of 1 minus q to the k. That's fine. So we still have a sum. These are just the numerators now. Oh, wait a minute. No, that's right. That's right. These ones start at n because of the numerator, or because of the top part of this argument. But this one starts at n plus 1. So I had divided by n through the previous, so that would cancel with this guy. It does. It should give you 1. So on the left, you still have these two. N through the previous. Does that make sense? Huh. You know, it's funny. Yeah, you're doing something wrong here. Yeah, you did this backwards. You should have written out this previous term. You would have seen it. This is wrong. Everything after this is wrong. Because this is, I started acting like it's increasing, but it's supposed to be decreasing upstairs. So what I'm saying is, this is missing that term. For some reason I thought of it the other way around. This is actually stopping one earlier than this. What I'm saying is I divided by a term that was not there. This term is still there. It makes more sense. So, all right, we got to start over. I don't have to start all the way over, but we have to start back here. So when you multiply by this denominator, right, it cancels on the first term. On the second term, it cancels everywhere. It does cancel everything except that there's an extra factor. So I'm going to jump to that stage, right? This was actually correct up to here. I think I see what it did now. So our left-hand side looks like n plus 1, 1 minus q to the n, down to this. And if you were to decrease one more in the exponent, then you'll get this n minus k plus 1. But we don't actually have that here. So this is our left-hand side. We're trying to see if it's equal to so this actually does have this term, and then it's got one more, right? That's how it decreases. Then the other term, coming from this guy, the other term has a q power next to it. It's also got a 1 minus q to the k now. But that one maybe looks a little closer to the left-hand side. Like starts here, ends there. Starts at n. Same story. Ends at 1 minus q to the n minus k plus 2. So it's also, in a sense, it's also short. It's missing that factor. Yeah, I made a mistake there. I canceled too much when I did this. So it doesn't have this factor, is what I'm saying. But instead it's got this weird new factor that we introduced when we multiplied by the denominator, and it's also got the power of q that we mentioned. So now if you want to start dividing, we can go for it. You may as well divide all the way up to here. So divide this, divide the next, all the way up through this. We're dividing. And on the left you'll be left with just this one. And we're trying to see that that's equal to, so you can divide by the n minus 1 all the way down to this. These are gone. So on the right you'll have this term, and you'll have this stuff. When you distribute this, you get junk minus q to the n plus 1. Okay, this is looking a little better. Oh, there's that junk. Wait, but we're adding it. Oh, all right, let's see what happens. When you multiply this, you get q to the n minus k plus 1 minus q to the n plus 1. And I guess I'm kind of happy because this is at least possible now. Oh, look at that. It cancels. Yeah, these are gone. Boom, we're done. Perfect. Why is this negative? Son of a... Why is this negative? Oh, no. Oh, because this is not supposed to be positive. It's supposed to be a negative. Good. Thank God. Yay. All right, so that was a straightforward way, a little more brute force with the algebra than obviously the easy way. Easy way is looking nice now, isn't it? All right, 60.5. I don't know how I'm going to show that this is a polynomial. Also, he points out that the coefficients are symmetric. But, all right, so nk is a poly of degree kn minus k in Q. Well, kind of a smart aleck comment. He says, well, it's clear for 0, right? I want to say this is 1, right? Yeah, it's degree 0 polynomial. So check. If you do 1, you'll get 1 minus q to the n over 1 minus q, right? Which is supposed to be a polynomial in n, 1 times n minus 1. Okay, so it's a polynomial in n minus 1, which is true. You're getting 1 plus q plus up to q to the n minus 1. So it's degree 1 times n minus 1. So it works out for this guy too. So it's true for k being 0 and 1. I happened to look at I skimmed the answer before. So yes, this is induction, but he must be using the previous, does he use the previous result? Because it's induction on k. Let's just see. Does he use 60.4 probably? He says, it's obvious, use 60.4. Yeah. Okay, so here's the thing though. You're getting, you know what? This is true for all n, what we just saw. Okay. So it would be true for n plus 1 as well. So like if I subtract this is the same as this stuff, which we can assume is a polynomial of degree whatever, right? But we also know that n plus 1 with a k minus 1 is a polynomial of degree whatever. So by hypothesis, by an induction hypothesis on k, this right-hand side is a polynomial, I guess its degree is, well, it's going to change, but it starts off as this part, this term, this factor is k minus 1 n minus k plus 1 is the degree. And then we're multiplying by this, so we're going to add n minus k plus 1. So that's our assumption, just by induction. Now we get a difference. I guess I shouldn't worry about that too much, huh? Yeah, if the difference of two things is a polynomial, then of course either one of these individually is a polynomial. So maybe I won't even address that. But I do want to make sure the degree checks out, I guess. How could it? This is a weird mess. Oh, I do get, normally we'd get kn minus k, so I guess here we're going to get like kn plus 1, something like that. Eesh. Alright, here's n plus 1 minus k. Ugh. N minus k minus 1. Okay, so we're looking at k minus 1 times n minus k minus 1. And then plus another n minus k minus 1. Right, so it's k times that. So the right-hand side is, it's annoying. I mean, it's not quite the right formula, right? Well, what were you expecting? I guess I was expecting, because this part's degree k n plus 1 minus k. And this part's degree k n minus k. Anyway, the best you can expect is this, right? This part matches up. And that's correct. That's the degree that it actually is, right? And that is larger than this, right? Yeah, sure. So this is fine. What were you expecting? I guess I just wanted to get a clean formula for this guy. But instead I proved it for n plus 1, which I guess is not a problem. Yeah, it's fine. You should stop thinking about that. So the last part of that is he mentions that the coefficients are symmetric. I don't know. How would we go about doing that? Use the initial definition, right, and substitute q the right. So if you use q inverse, like basically look at this, he's saying these will be equal. Huh. Is that true? if you had 1 minus q to the negative n, 1 minus, this decreases, so it actually is like a plus 1. And then downstairs, instead of q, we have q inverse. So this is normally n minus k plus 1. For us, it's backwards, right? N minus k plus 1. N minus k plus 1. All right. So, of course, we could multiply by, I don't know, q to the k over q to the k or something. Like, how are we going to make this? Well, no, there's still k factors everywhere. So yeah, just multiply by q to the k over q to the k. No, that doesn't quite work. That doesn't work. Because q only fixes this part. Maybe you can factor, and I'll have a bunch of q's, and downstairs I'll have something that starts at q to the k and decreases. That's in the numerator. So it's clearly not the same formula. Huh. Must be missing something like this. Yeah, so his answer was just, for the clause about symmetry, just use the initial definition and substitute q inverse, like reciprocal of q, not q inverse. Sure, reciprocal of q for q. So for some reason I was expecting these to just be equal. But does that even make sense that they would be equal? I mean, do maybe a small example even, right? So like, is this equal? If you had like 1 minus q to the negative n over 1 minus q inverse. If I multiply q over q, I mean, okay, you could do q to the n or q to the n, and you'll get I don't know. You'll get some junk that makes no sense. Yeah, they're not equal. So what you will get, though, this is the original, right? Q to the n minus 1 over q minus 1. Yeah, there you go. So here is the original. So like, if I take, here's another way to phrase it. Q to the n minus 1 times n1 in inverse gives you back n1. And q. Oh, sorry. This is upside down. The negative of that. Or, you know, q times this gives you q to the n times this. So we have it more generally. That's okay then, I guess. It's not as symmetric as I thought. I thought it was just going to be 1-to-1, but if I multiply by like q to the sum of these numbers, right? So q to the k times k minus 1 over 2. It changes the denominator to be, it transforms the denominator to be the usual one, this one. And then upstairs, I mean, I can do the same thing, but it's an even bigger sum. We're starting at this number, and we're summing up to n. So you get the same kind of relation. You get q to the sum times the inverse part equals q to an even bigger sum, starting at n minus k plus 1 and summing up to n times this. So we get, the point is you get a very similar statement to this. No, I had it right the first time. Yeah. I had it right the first time. It's not the negative of this. It's right. This is the original. If you divide it by q to the n minus 1, you'll get the stuff we started with. So this was right. So yeah, these are the other way around. This is a 1, this is an n. And of course this is that easy case of just a sum. So it's saying, like, if you multiply this sum by q, it's the same thing you'll get if you take the reciprocal, well, and then multiply by q to the n. That's probably true. Yep, it is of course true. So if we know it's a polynomial and we know that multiplying by some fixed power of q gives you the same polynomial, isn't that enough to tell you that it's symmetric? Yeah, so if we sum these, like n minus k plus 1 plus n, you get 2n plus k minus 1, right? So we have k over 2 of those. Like I can multiply this by, on the denominator we can multiply by q to the sum from 1 to k. Looks something like that. Oops, 1 over 2. We can just multiply that on the top and the bottom. So you'll get an extra one of these in the numerator. But downstairs it'll have transformed into the right-hand side formula. Upstairs we're going to do the same kind of thing, but instead it's, starting at yeah, that's right. So I'm taking the negatives of these. We're starting at, say, n minus k plus 1, and we're adding n. So you get 2n minus k plus 1. That's the sum that you get, and you do that. There's actually k factors here, so we're going to do this k over 2 times. So that's the formula I would expect upstairs. If all you did was multiply by these, you immediately get this back. So we're saying that this I guess I'm saying that if you took q to the k over 2 times 2n minus k plus 1, if you multiply that by and choose k q inverse, it's the same as multiplying the sum times the usual. That's the formula we get this time. And apparently that's enough to prove that it's symmetric. I'm going to have to think about that one. But this has been going on kind of long, so I think I'm going to stop there for the day. I'll think about this a bit. So another thing is we know that these are both polynomials of this degree. And we're just saying if you multiply this one by this amount, we actually didn't change the coefficients, we just sort of scaled the powers. I guess that probably is enough to just conclude that it's symmetric. You know, it's like analogous to saying if I took x to the k times this polynomial and x to the k prime times another polynomial, they're equal, and I know that the degrees are the same. Well, no, there's a little more to it than that, because this q is, it's more like you're doing this, p of x inverse. That's why it's symmetric. Um, hmm. Yeah, that's not quite that. That's not very clear, huh? Hmm. Yeah, I'm not sure on this. Uh, well, wait a minute. So what exactly is this Q? Um, we've got. I'll just make new room for it. The guy with the reciprocals, we're multiplying by what? It's Q to the k over n, or 2, excuse me. Is this 2n or n? Yeah, 2n minus k plus 1. And then we're subtracting from that k minus 1. Right? If we divide by this, we are subtracting this fraction. So I should have just written, anyway, we're subtracting k minus 1 in parentheses. Like that. So plus 1, okay, fine. So it's 2n minus 2k plus 2, right? Or in other words, k times n minus k plus 1. So this is what's being multiplied by your degree. It's n choose k, right? So it's this degree, k n minus k, poly in the reciprocal. Why is there an extra? I don't know what this 1 is doing there, you know? That's my only. So for example, we looked at the example of n1, and we found, like, if you multiply by q to the n minus 1, you get the original guy back. Right? Just as a small example. That's this case, of course, with k being 1. By my formula, I should have had q to the n So is this wrong? I could be off by 1. But in any case, this kind of made sense. All right, I'm gonna have to think about it again, because now I'm like wondering why that even helps, right? You're just saying that. Oh, yeah, it does help, because it's not like a, when you take q inverse and you multiply by q to the n minus 1, well, say you take the 1 from there, you get this guy. So it is, we are showing that it's symmetric. The fact that it's equal means all the coefficients are, it means exactly that they're symmetric. And we know it's polynomial, and so, yeah, that would be enough to show it in general, because the larger terms, like the larger degree coefficients in your originals, are coming from the smaller degree coefficients in your reciprocal. Yeah, that makes sense. So my only issue now, I don't think there's really much more to say. It's just, is this the right power? Because it doesn't agree on 1. They seem to have gotten it wrong. I'm telling you for 1 it gives you q to the n, and that's not actually quite right. And it also couldn't have been right? We should be getting, I would think we'd be getting this. Am I off by 1? So we're also supposed to get, yeah, this is correct. This degree is correct for like this polynomial. So yeah, why wouldn't I get an extra 1? Did I screw up this addition maybe? If this 1 wasn't there, I think, well no, because I would need this to be gone too, right? This is for sure there, that k minus 1. Well, usually I don't do it that way. I didn't use the same formula. Yeah, this is wrong. These are not consistent formulas. K over 2 times k minus 1. So like, here I would do k plus 1 times k over 2. That's what I would have written normally for the formula. Right? Let me just see. I keep using this shortcut of k times k minus 1, which is probably not wrong, but say you add up like 1 and 2 and 3 and 4, right? Here k is 4, I thought. So you're getting k plus 1 times k over 2. Yeah, why do we keep using, I guess I just have the wrong k value, right? If you go to 5, I guess. If you went to 4 and if you treat k as 5 for some reason, then, well, so maybe this was wrong. Maybe I meant to put a plus 1 here. I mean, I definitely did. So what if we replace that with a plus 1, does it fix my problems? It does. Yep, it does. All right, fine. So I guess my little summation formula was off. Make this k plus 1 instead. And what will happen is we get plus 1 minus 1. This is gone. We get the correct q value. And that q scales your polynomial of degree that in q reciprocal. So you know that it now is a polynomial in q. And you know that they're equal. and you observed what it's doing, like your higher degree coefficients are coming from the lower degree coefficients over here, and that's why it's symmetric. So I'm not going to say anything else about this next time, but that was the end of, that was 60.5, the symmetric comment. K times n minus k. Oh yeah, there you go. K times n minus k. Yep. Yeah, that's what I observed. I didn't write it down like that, but interesting. So it's a symmetric polynomial. Well, it's a polynomial with symmetric coefficients anyway. All right, ladies and gents, thank you for tuning in. I'm going to disappear. You have yourself a great day.